Today, we will learn everything you need to know about piping system. In just one short video, we will teach you the simple trick to visualize and solve any kind of problem related to piping. You will learn about every type of available systems, how their curves are drawn, and what these curves represents, and how to use them. When you make any kind of change, like you open or close a valve or increase the discharge pressure, or even you change the pipe diameter or material. The goal of this video is to create a mind map that helps to visualize and predict, so stick till the end of this video to master everything about piping system. There are usually 4 ways by which we move fluid in piping systems. The first is by gravity, in which liquid is stored at higher elevation to produce desired flow and pressure. The second method is by pressuring the fluid supply tank by gas. The third method is by the use of centrifugal pump in the system. And the final method is by the use of positive displacement pump. These are the 4 most common ways of transporting fluid. You are probably familiar with system curve and pump performance curve, and know how useful are these to predict the flow rate and pressure in the system during the designing phase. But what you may not know is that they are equally useful during the operation phase of the system, and today that is exactly we are going to learn how to use them in solving and visualizing everything that can happen to piping system. The system curve is same for all of these 4. However, except with a few minor changes for by gravity and pressurized tank system. But the curve for the way we pressurize the fluid is different. The curve for centrifugal pump looks like this. The head is decreasing as the flow rate increases and vice versa. The curve for the 2 types of system on the left, that is by gravity system and by pressurized tank system, are same. No matter how much you open or close the valve to regulate the flow, pressure supplied by the tank remains the same. The curve for our last type, that is positive displacement pump, is a straight vertical line that represents the built-in characteristic of these pumps, which is to pump the fluid at a constant flow rate irrespective of discharge pressure. Let's first look into these 4 curves more closely to understand clearly what they represent. First, let's start with the system curve. We will use this system as an example to understand system curve. Here, as you can see, pump is sucking water from a tank and pumping this water at higher elevation through discharge pipe. Notice the valve that control the flow. Since the valve is closed, the flow stops. To draw the system curve, we will take flow on horizontal axis and head on vertical axis. Since there is no flow in piping system, that is, the flow is 0 but the head is not 0 here. The head here is equal to the difference in the elevation of suction and discharge plus the difference of the pressure at these 2 points. This is called the static head. The head of fluid, when there is no flow. Let's place this point on graph. This point represents static head. Now if we open the valve, water starts flowing. So friction is developed between the flowing water and stationary pipe. Faster the flow, more will be the friction and vice versa. Now to produce this flow, pump must overcome not only the static head created by stationary fluid but also friction head created by moving fluid. Now the pump develops pressure at its discharge that is greater than static head, by the amount equal to head loss by friction. Here it is indicated by P3. Now we can place this point on graph. If we increase the flow, the friction will increase. To overcome this, pump will have to supply more pressure, and the pressure P3 at its discharge will increase further. Now we can also place this point on graph. If we join these points, we will get system curve. So the system head curve begins at the total static head, that is the static pressure and elevation at discharge minus the static pressure and elevation at suction. So if we change the total static head, the curve can shift up and down. If we increase static pressure or elevation at discharge, the total static head increases. Curve will shift upward. And if we increase static pressure or elevation at suction, the total static head decreases. The curve will shift downward. Now we open the valve, the total losses in system decreases. So the slope of the curve also decreases. Decreasing the length of pipe, increasing the pipe diameter, reducing the number of fittings, or even changing the pipe material with the one that has the lower roughness, also decreases the curve slope. And if we close the valve, or there is some restriction to flow, like debris or air entrapment in the system, total losses in the system increases. Then the slope of the curve increases. Similarly, if we increase the pipe length, reduce the pipe diameter, increase surface roughness, or adding more fitting in the system, the slope of the curve increases further. Now let's first look at the system with the centrifugal pump. We can superimpose the pump curve on system curve. At the point of the intersection, we can read the values of fluid flow rate and the pump discharge head. If the pressure or the elevation at the discharge increase, or the pressure or the elevation at the suction decreases, the total static head of the system increases. So the curve shifts upward. Now the flow rate in the system decreases, however, the head or energy added by the pump to fluid increases. Note that here we are talking about the head or energy supplied by pump to fluid. We are not talking about the pressure at the discharge of pump. And the curve will shift downward when total static head of system decreases because of either the elevation or the pressure at suction increases or the elevation or the pressure at the discharge decreases. Flow rate in the system increases, however, the energy or head added to fluid by pump decreases. Again, note that we said head or energy added to fluid. We didn't say anything about pump discharge pressure in our discussion. And if we open the valve, total losses in the system decreases, and the slope of curve also decreases, giving us higher flow rate and lower head or energy will be added to fluid by pump. And if we close the valve, total losses in the system increases, and the slope of curve also increases, giving us lower flow rate, but pump will have to add higher head to fluid. Now let's take the case of the system with the positive displacement pump. The curve of positive displacement pump is nearly a vertical straight line. At the point of intersection, we can get flow rate and discharge head value if the pressure or the elevation at the discharge increase, or the pressure or the elevation at the suction decreases. The total static head of the system increases. So the curve shifts upward. The increase in head of fluid by pump will be higher to cope up with increasing total static head. However, in any case, it maintains its flow rate at a constant value. And the curve will shift downward when total static head of system decreases because of either the elevation or the pressure at suction increases or the elevation or the pressure at the discharge decreases. And if we open the valve, total losses in the system decreases, and the slope of curve also decreases. Because of this reduction in losses, the pump will have to add less head or energy to fluid to maintain flow rate at approximately fixed value. And if we close the valve, total losses in the system increases, and the slope of curve also increases. The pump has to add more head or energy to fluid to cope up with these increasing losses and maintain flow rate at approximately fixed value. But what will happen to pump discharge pressure in this case? Tell us in comments section below. Finally, we will take the case of bi-gravity flow system, in which fluid is flowing from higher elevation to lower. Its curve is horizontal straight line. When the level of fluid in upper tank decreases, or the static pressure over the surface on the fluid decreases, then the curve shifts downward, and the curve shifts upward when the level of fluid in upper tank increases, or the static pressure over the surface on the fluid increases. And if we add up exactly the same amount of water that is lost by the tank, then the water level will not change and the curve will also not move. Now let's place the system curve. As we have already mentioned, the system curve is slightly different here. The curve begins at static discharge head only, that is the static pressure and head at discharge. At the point of intersection we can read the value of flow rate and head requirement. If the static pressure or gravity head at discharge decreases, total discharge head decreases. The system curve will shift downward towards the high flow rate. And if the static pressure or gravity head at supply increases, the supply curve will shift upwards, because of this increasing head and towards higher flow rate. And the supply curve will shift downward towards the lower head and thus lower flow rate when static pressure or head at supply decreases. Likewise, system curve will move upward towards lower flow rate when total discharge static head increases either because of static pressure or gravity head at discharge increases. Now if we open the valve, total losses in system decreases and the slope of system curve also decreases, giving us higher flow rate. Now if we closes the valve, total losses in system increases and the slope of system curve also increases, giving us lower flow rate.